Hi, this is John O'Hanion from AVID LLC, here to give a demonstration of AVID OAV, our multidisciplinary design and optimization software for ducted fan vehicles. This program can run on Windows, Mac OS X, and Linux. Today we're going to be looking at an example vehicle, this ducted fan here. It's a very conceptual level vehicle that just has minimal components in it, but it gives a good idea of the capabilities of the AVID OAV software. Here you'll see that the vehicle is comprised of a duct, a fan, a fuselage, some side pods, and some control surfaces in the back. As your design would mature, you would start to see more detailed components like engine struts or landing gear, a stator, other electrical components, things like that. So I'm going to turn off the coordinate system axes and turn on the CG marker, or center of mass, center of gravity. This gives you an easy way to visualize your geometry and your layouts. Each component in the geometry seen here is described in this tree view over here. Each component has parameters that define its shape and position. So right now I have the duct selected. You can also select components from the display, and you'll see that the propeller is now selected. Over here in this pane you'll see the location of the component, the rotation or orientation of the component, and also you can select the tab for shape parameters. This is component specific. These are for the propeller. You'll see things like number of blades and the chord length at the tip and the root, the diameter, which is linked to the propeller design variable for optimization. When you change a value here, either through the slider or through entering a value, you can see the geometry update in the window, which is very intuitive for creating your model. Now I'll demonstrate how you can add a component to your vehicle. So I'm just going to take a component out of the available components catalog down there, and I'm going to position it so you can see it. It starts out pretty small. Oops. And then I'm going to start changing the size of it so you can see how easy that is to do. So I'm just going to make it a little bit bigger here. And then I'm going to go in and change the cross section. So now I have a pod that might represent some sort of sensor or instrumentation, some avionics, some bump on the outside of the duct. It's fairly easy to create that geometry, but one extra thing that comes along is you can easily calculate the mass properties if you supply a density, and if it's a thin shell object you just supply a thickness, and then you select from one of these algorithms here for calculating either the solid mass properties or the shell mass properties. So once you select one of those, it will calculate the weight and the center of mass or center of gravity here, and the moments of inertia. You can also apply margins to the weights and such. So that demonstrates how easy it is to create a component in your vehicle. I'm just going to delete this. And the next thing I'd like to show are some of the other aspects of the modeling that are not necessarily geometry based, but are still important for the vehicle design. So next I'd like to show payloads. Let's look at electronic payloads. I'm going to add a camera to the vehicle. The purpose of these is to represent the weight and power consumption of all the electronics that you have on the vehicle. You could add avionics, communications hardware, generic components. I've selected one from a predefined catalog, but this is customizable, so you can create any kind of component that you desire. Another important aspect of modeling your vehicle is the propulsion system. So we have installed in this vehicle a small turbine engine, and likewise again you can select from a catalog of different ones, or you can create your own engine if you know the specific characteristics. You'll see that each engine or motor can specify the fuel consumption, specific weight, the overall weight and power, RPM, all the different characteristics that you would want to specify for a propulsion system. And we can model electric motors, piston engines, rotary engines, and turbine engines. Other things that you might want to include would be some of the accessories like starter motors or fuel tanks. We can model batteries, propulsion batteries, a generator or an alternator to start the engine, and other power accessories. Some of the other modules that are available are the Aerodynamics, which I'll speak about soon, engine modeling, which gives the ability to use a response surface model of the engine, mass margining to add margin into your design, point performance, which is things like your turn performance, your instantaneous climb performance, things like that. There's some geometric options, some performance options. There's a linearized model of the 3 degree of freedom dynamics of the vehicle that allows you to assess stability. And then weight and balance. This is the total weight of the vehicle and the corresponding moments of inertia and the center of gravity or center of mass of the vehicle. And that's built up from all the components, mass properties, all the electrical components, fuel, batteries, and such. Let's take a look at the aerodynamics module. This gives you the ability to evaluate the aerodynamics of your vehicle like a virtual wind tunnel test, in a sense, where you can specify a range of velocities, a range of control surface deflections. You can specify the RPM of your motor. You can specify these aerodynamic angles, and then you can run the analysis, and you'll get a large table of numerical data that you can use to export to Excel or to MATLAB for simulations externally. This is how we would create a model for like a 6 degree of freedom rigid body simulation. Other export options include exporting the cross-sections as a Hermite file. You can export the geometry to an IGES file that could be imported to CAD. You can also export images. The next thing I'd like to talk about is the mission analysis, which is represented by this dialog down here. Each of the components in the vehicle calculate aerodynamics based on parametric equations, and those values sum together in a build-up to represent the aerodynamics of the complete vehicle. In each phase of the mission, the aerodynamics and propulsion and control vane deflection are all evaluated to find a solution, and each phase, the velocity, altitude, time, and distance will correspond to either a fuel burn or battery draw, and then you include several phases to make up a mission. So this mission starts out with a high altitude climb just to check to make sure the power is sufficient. And then it starts from a hover at 10,000 feet, which is sort of like you're idling on the ground. And then you would climb at 10 feet per second from 10,000 feet up to 10,500 feet. And then we want to cruise at roughly 85 feet per second, that's 50 knots, and we're going to cruise out maybe 8 kilometers or so. And then we're going to hover for 45 minutes and then cruise back and hover to simulate a landing. So let's compute the mission results. And what you can see here is a very large report of data, basically all the data that comes out of each phase, and you can select how much data you want to see in your report, and there's also some quick links over here on the left. So first you see the flight conditions for each phase in the columns here, and the first thing that's fundamental to the mission is each phase it solves for the orientation for trim or equilibrium. So when you're cruising, the vehicle is going to tilt over some, and there's also control vane deflections needed to cancel the moments in those conditions. Each phase will report the lift and drag, pitching moment, lots of different parameters in here, the control authority, the pitch vane, trim deflection. In propulsion, you'll see things like how much power was required for a particular phase, the RPM used. In this case, this is a variable pitch propeller, so the pitch angle on the propeller, what specific fuel consumption and how much fuel has been burned, and then each component reports its own aerodynamics that go into the build-up of the aerodynamic forces and moments. So this is the duct here. There's also mass properties. As you can see, there's a lot of information available from the mission analysis, and a lot of these pieces of data are available for optimization, either design variables or included in the objective function. They could also be included in trade studies. Next, I would like to show how you can use optimization within this framework to find the best solution for your mission. So opening up the optimizer dialog, you'll see there's 3 sections here. The first section defines your design variables, so we have several selected here. Only one is enabled for varying. The next section is the constraints. Here we have a sufficient fuel to perform your mission, sufficient engine power, and finding the force balance or equilibrium. And finally, down here you have your objective function that you're trying to either minimize or maximize. In this case, we have the total fuel weight. We're trying to minimize the total fuel weight to perform our mission, and we have that design variable open, and we want to find the value of fuel that satisfies all the constraints. The constraints you can see, one is violated, one is active, and one is satisfied. Violated means that you have not found a feasible solution for that constraint yet. Active means that you're right on the border of that constraint that you asked to satisfy, and satisfied means that you're well within the bounds. So let's run this optimization. This is a 1D optimization that doesn't take very long to find a satisfactory answer. So I'm just going to stop it prematurely. And you can see now that both constraints are active, meaning that we are right on the limit of the right amount of fuel for this mission, and we have just enough engine power to perform all the required maneuvers. Now that was a simple optimization. You can do multi-variable optimizations by enabling these or selecting other variables to use. And those obviously take longer, but it's very powerful for finding solutions to the nonlinear problems that you see here. Next, I'd like to show the trade study functionality.
While the optimizer helps you to solve for a specific case or find a solution, the trade study gives you the ability to vary some independent variables in this section up here and look at how they affect some objectives or dependent variables defined down here. So in this case, we're looking at the cruise velocity from phase 4 in our mission and varying that from 10 feet per second up to 110 feet per second and seeing how that affects these parameters down here, which include the pitch control vane deflection, the lift and drag, the angle of attack, or alpha, and then the thrust limit, the actual thrust, and then the power required to produce that thrust. So let's perform the study. And what you get is a table of data here in the bottom, and you can copy this to Excel or other external applications, but you can also create graphs here in OAV. So first, let's plot the angle of attack. And I'll add a plot of the lift and the drag, and we'll also look at the control vane deflection, and also the thrust limit and the thrust available. So looking at the angle of attack, the independent variable here is flight velocity. If it were 0, that would be hover, and we would be oriented 90 degrees from horizontal. So as the velocity increases, the vehicle tilts into the wind for higher speed flight. That's important for interpreting this graph of lift and drag. If you're familiar with wing aerodynamics, you would expect the lift to increase with velocity, but the drag to increase quadratically. And here we see that's not the case. The lift is increasing while the drag plateaus to a value and actually starts coming back down. And that's because of the large change in angle of attack. As the vehicle tilts into the wind, there's less drag and you're producing more lift and thrust. In this plot we see the pitch control vane deflection, and this corresponds to the pitching moment that the vehicle experiences, and these control vanes are counteracting that to produce a net of 0 moment on the vehicle to attain equilibrium. So from hover it would be 0, and then it comes up through this hump region right here and then decreases again. So this region here is the transition from hover to high-speed flight, and that's where the largest control vane deflection or control allocation you'll see. And that serves as a design case for vehicles. So you can use the output from your mission to help size particular portions of your vehicle. And finally, we look here at the thrust limited by RPM and horsepower, and the actual thrust required by the vehicle. And you can see that in all cases we have more thrust available than what was necessary for the mission. So this export button allows you to save your results to an external file that could be used in other studies. This kind of analysis could be adapted for quad rotors, helicopters, or fixed-wing vehicles to give you a multidisciplinary design and optimization framework. If you'd like more information about AVID OAV or AVID's capabilities and other software products, please visit our website at avidaerospace.com. Thank you.